All right, when we're looking at circular motion, we want to start by describing angular motion. So this is looking at this question of, in physics, how do we describe the idea of spinning in physics? And so in order to define that, we need to talk about angular quantities. So first, we want to talk about the rotation angle, and this is just how much something has spun. So you can think about it as basically position, except with angle instead. So once you've gone this far, that's a rotation of theta. If you've gone to here, that's 2 theta, 3 theta, etc. So this is measured or typically represented with the variable of theta, and the units of radians. Angular velocity is how quickly the angle changes. And that we represent with the variable omega, which is like a little loopy lowercase w. And units of radians per second. And then with angular acceleration, this should be pretty clear how quickly angular velocity changes. So just like position, velocity, acceleration, but now we have kind of angular position, angular velocity, and angular acceleration. This variable is the lowercase alpha, and units of, radians per second squared. Just like with position, just like with linear acceleration was meters per second squared, this is radians per second squared. And again, this is the lower Greek letter alpha. So if we want to relate this to linear quantities, we're going to end up using the relationship here. And if you didn't know this, 1 radian is defined as the angle where delta S and R are equal. So if you have an angle of 1 radian, that means that your delta S and your R are equal. And this is why when you go all the way around, that's going to be 2 pi degrees or 2 pi radians, and it'll be 2 pi R for the S. And so that's why this kind of relationship works out. And so what that ends up meaning, for all intents and purposes, is that the angular quantity is equal to the linear quantity divided by R. Or in other words, you have the one that's, blanking on this, theta times R is equal to, we'll say delta S or delta X in this case. You have V times R, omega times R is equal to V, and alpha times R is equal to A. Let me just double check those because my brain is feeling a bit fried at the moment, so I'm just pulling up my notes to double check to make sure that those relationships are correct? Yes. So you've got this position is equal to theta times r, velocity, linear velocity is equal to omega times r, and linear acceleration is equal to r times alpha. You can also reverse these around if you wish. Theta is equal to delta x over r. Omega is equal to v over r, and alpha is equal to a over r. And this is just, again, because of this relationship here. If we see that we've changed by delta s, that's going to correspond to some delta theta change here. And then when we take the derivatives with respect to time, for those of you in calculus, or for those of you not, when we just look at the changes over time, well, these change at the same rate, and that means the velocity is going to be the same kind of proportion, the acceleration is going to be the same proportion. So that, I believe, is our last idea here in kind of this introductory section of looking at angular quantities.